expert webinar. Yeah, this would be my first comment, as you may see it on your screen already. This webinar will be recorded and will be distributed across the YouTube channel of EAGE. If you're feeling unconfident, you should switch off your camera. Right. Yeah, this is our first webinar on the experts discussion group within the geomechanics community in EAGE. And actually, it's our first, our first webinar in total, because we are very new. We are the new kids on the block here. So let me quickly introduce ourselves, who we are, what we aim at, why we found this community, and also how you get in contact with us. So the community was found in end of 25, and now by now we already have almost 700 people in our LinkedIn group, where we try to update every now and then on what's happening in the geomechanics group and network, where we like to share knowledge and also develop the next generation of people. Main topics are, of course, knowledge exchange, also to get younger students interested into geomechanics, to develop them, to help them getting in our topics, which are, for example, the subsurface energy system, or including, of course, everything from exploration down to store and dispose remnants, but also, of course, now these days included into the energy transition. On top of things, we are aiming for also developing tunneling and mining sector geomechanics in this community, develop new connections between all these groups. So who are we? The committee originally was established by Elke, who is also in the call and who is the chair now. And we were roughly 20 people who like to have this community, because geomechanics is an important topic in all the environments I explained before. And so we are now central group of roughly 10 people working across the different sectors and in Europe and Near East. So how do you, what are we doing and how do you get in contact with us? Well, we are in the EAGE annual. There you can reach us, get the people face to face. We are hosting educational networking events like the webinar series, like this one, where this today it's MineHeat networks, and next time will be May 20th, where we will have a webinar hosting 3 experts on the topic of hydraulic fracture simulation and tight rocks. And also we will post across LinkedIn the news and vacancies we are gathering in our community. And it's also in planning to have a development network for younger members. So, of course, next big thing where we are present with the committee is at the annual in Aberdeen, starting of June. So if you would like to talk to us, please get in contact. Otherwise, you always can also reach out to us through LinkedIn, through emailing also. And of course, we will be present at the GET 26 in Hanover, which takes place in November. So if you are not a member yet in the LinkedIn group, you please join us for the geomechanics community. And of course, thank you to be here today. We have two wonderful people showing us or telling us about mine water heat usages. These are Elke Mugova from Fraunhofer EAGE and Gareth Farr from the Mining Remediation Authority. Give me a quick introduction to them. Elke is a mine water researcher and studied originally hydrogeology and engineering geology. She's working now for 1 year in Fraunhofer EAGE in the European Union project Push It, where she has the responsibilities of stakeholder engagement, community communication, and dissemination. Not only she contributes by presentations these days, but she's also the General Secretary of the International Mine Water Association and Women in Mining and Resource in Germany. So she's organizing a lot of national and international symposia and conferences. As a second guest presenter, we asked Gareth Farr came to us, and he is a specialist also in Mining Remediation Authority in Great Britain, where he's involved into a lot of different projects. For example, the Gatesheads project, where he will show us something about. He will show us a bit about today. He has been working before in the Mining Remediation Authority and in the British Geological Survey. So Gareth is a chartered geologist with more than 20 years of experience in the energy sector. What would be the agenda today? We will have a quick introduction 101 on mine water heat, then a poll held by Elke. Then we will have operational mine heat schemes presented by Gareth, and on top, Elke will join in again with mine water geothermal storage. All of this will be concluded in a panel discussion with the two of them, where I will be the moderator. My name is Peter Pancic. I'm also from Fraunhofer EAGE. If you feel you have questions in between the talks, I would be happy if you can put them into the chat. And I will ask you during the panel discussion to unmute yourself and ask them directly. And of course, any question, any discussion point which comes up during the discussion will be signaled by the hand. So I would open the floor for Elke, give us a few slides overview on mine water heat. Thank you.
All right. Good afternoon, everyone. I hope you can hear me. Now let me try to share my slide. Here we go. Maybe Peter, can you signal me quickly if everyone can see the slide? All right. So now, just need to look at this screen. All right, so 101 mine water geothermal. I thought about to give you a quick introduction because not everyone is familiar with the topic of mine water, nor mine water geothermal. So I thought let's start rather with the basics, and then we go a little bit more in detail, and Gareth will talk about practical examples. So most of you, I guess, are geologists, but maybe you're not aware how mine flooding works. So maybe first of all, we need to look at a schematic image of an underground mine with the shafts and horizontally with the galleries. And during active mining, when mining activities are done, groundwater is always flowing inside the mine. So they have to pump the water, the groundwater, or then the mine water out of the mine. But then in the decommissioning phase, when the mine is closed, the water is still flowing inside the mines or inside the mine, but the pumps are switched off. So the mine water table is rising, and after years or decades, it really depends on the mine, on the size, and on the structure of the mine is flooded towards a certain level. This can sometimes be up to surface level, or this can be up to dewatering added. So it depends, but usually it takes years to decades until a mine is flooded. But now we want to talk about geothermal, and as you all know, there's the geothermal gradient in Europe around 3 Kelvin per 100 meter, and this is depth dependent. So only around the first 20 meters of the surface are influenced by climate and weather, but then deeper down is really the geothermal gradient that influences the temperature of the water. And because we have the geothermal gradient there, the water inside the mines is warm. Depends a bit, but you can say roughly in 1000 meters, 30 degrees Celsius. So how can we access the mines? And I have a little figure here for you as well, and I would like to go through the figure from the left side to the right side. So I already mentioned drainage adits. A lot of mines, even underground mines, and especially historic mines, so before 1900 and earlier, they have drainage adits because it was much easier to drain the water outside of a big mining system instead of having pumps everywhere. So the water nowadays is flowing out of the mine, and you can place a heat exchanger there and just get the water from this natural outflow at a drainage adit. Then there are closed systems. Closed systems is the same like closed systems you have in boreholes. Just in this case, we have the closed system with an exchange liquid inside a flooded mine shaft. And then open systems, which are much more common in mine water geothermal. And this can be different scenarios where we can have open systems. So the first option is to have it in combination with mine water treatment. So in a lot of regions in the UK, here in Germany, but also in other countries, the mine water needs to be pumped and the mine water needs to be treated. So there are different options to place the heat exchanger. Either it can be placed before the treatment plant. Obviously, the water temperature is higher, but also the water quality is usually not as good. That's why we have mine water treatment. So, need to consider that there are larger scaling or fouling effects. Or you could place the heat exchanger after the mine water treatment, lower water temperatures, but better water quality, so less scaling or fouling effects. Then we can access the flooded mine body via open shafts. And you can see this can go in both directions because we talk about mine water heat, but actually I think it's better to talk about mine water geothermal because mine water can be used for heating or for cooling. So as I said, in 1000 meters around 30 degrees Celsius, but this really depends, just as a rough number. So if you take the water from the lower area of the mine, you usually use the water for heating, and if you take the water from the shallower area of the mine, you can use the water for cooling, and this can also be done in a system where you have heat extraction in the winter for heating, and then you inject the water back into the mine. That's why the arrows go both directions. Or in summer, you can extract the water for cooling and then inject it back into the mine. So if we have no shafts available that we can use, it's also possible to drill inside the mine workings. This can be the normal vertical drilling, but it can also be done via directional drilling. So for example, here you can't just drill vertical because there are buildings, infrastructures. So it's also possible, and we've done this here in Bochum with directional drilling. And then one specific user case is the MTES, the Mine Thermal Energy Storage. I will explain this then in the second part of my presentation, but basically it says that we can utilize a mine as a big geothermal underground battery. So we can store excess surplus heat from different sources, from solar thermal panels or from industrial surplus heat inside the mine, and then access the heat again when we need to use it. How it works here, a little bit more of a detailed figure how mine water geothermal works in general. So I already said we can extract the water, for example, via borehole, and then it's very important we don't use the mine water to heat the buildings. We always use heat exchangers, and this can be plate heat exchangers or pipe heat exchangers. Different options are possible. And then usually the water is not as hot to use it directly afterwards. So we need heat pumps to heat the water up to, well, depends, 60, 90 degrees Celsius. And then the cooled down water after the heat exchanger usually can be either discharged into the next river or into the ocean, or it can be injected back into the mine, which is the usual user case, so that you really have a circulating system here. As I said, we always have to consider we use heat pumps and we use first heat exchangers and then we use heat pumps. So this is the heating or cooling option with mine water geothermal. Or when surplus heat is available, we can do mine thermal energy storage. Above surface, because obviously we have the mine and we have the infrastructure of the mine, but then we also need to think, what can we do with mine water geothermal on the surface? So the first facilities we had was just heating single buildings, like for example in Germany, a fire brigade, a school, a municipality building. But for example, in Heerlen, that's in the Netherlands, there is a project in this town called Heerlen from the company Mine Water, and they have a 5th generation district heating network. So they use cold mine water, hot mine water, but also ATES, aquifer thermal energy storage, or borehole thermal energy storage systems to heat the whole city with this 5th generation district heating. So the idea is to use all the surplus heat, all the excess heat, and see where heat is available and where heat can maybe be stored. And this is, I think, really interesting also for the future of mine water heat, that you don't just look at small systems where you only heat one building or a small complex, but that you really can use mine water geothermal to heat an entire infrastructure, or maybe not purely use mine water geothermal, but to have it for the base load. But if you have more questions about the subsurface infrastructure, I can recommend to get in contact with my colleague René Verhoeven, because he is the expert for the subsurface infrastructure, and he actually also worked in this Heerlen project in mine water. Okay, a small overview about the technology, so just that you get an idea what's going on in Europe and in the world. Most mine water geothermal plants were installed since the 2000s, and data from last year from a publication says that there are 51 known plants worldwide, and 61 are in the planning phase, so quite a lot, I would say. And most plants have actually quite a long service life. So, for example, there's one in Eastern Germany in Ehrenfriedersdorf with it's functioning now for over 25 years, and only 11 plants are no longer in operation. Although these numbers are a bit wonky, so we're not really sure, because sometimes the operators don't give out clear data or clear numbers. Yeah, here you have a figure, and maybe if you want to scan in the QR code, this is this publication. It gives a really nice overview of the facilities, of the mine water geothermal facilities worldwide. And you can also see it at the map. So we have quite a lot in the UK. Gareth will talk about it. In Germany, if you're in the Netherlands, and here you can also see Poland, Czech Republic, yeah, and in Spain. Spain is also leading in mine water geothermal. And now my last slide, just to give you a short overview again, what sort of plants we have in Europe. So, for example, in the UK, in Glasgow, we have the Geoenergy Observatory. This is a research facility to test different scenarios with heating and cooling, and a lot of monitoring systems are installed there to really understand the system. Then also a huge focus in the UK is to utilize mine shafts as storing facilities. So not to go into the flooded mine voids, but only into the mine shaft. And yeah, well, they can have quite big diameters up to 9-10 meters. So it's a large flooded void that can be utilized. Then the geobattery concept, also really interesting. What is it called? Gareth can tell us probably. I forgot now, but it's a project where there is a data center here, and the data center has a lot of access galleries to calories. It came back to me. Galleries to calories. So there's a data center, and the excess heat from the data center is injected into the former mine workings, and then the idea is that the heated water is transported to the nearby city. It's a few kilometers distance, and then the city can access this heat from the flooded mine that was even heated up more by the surplus heat from the data center. Then abstraction and discharge. This is what I told you already with the galleries. This is quite a common and very easy concept because you don't have to install extra infrastructure. So you just basically can put your heat exchanger there, but the gallery is there already and you don't have to drill. So this is really cost effective for smaller facilities. Then Gateshead. Gareth will talk about it, so I won't say too much about it. Then I said in Spain, they have quite large facilities as well where they access a flooded underground mine, a coal mine, and they heat and cool the entire city with it. But in the Spanish case, they don't inject it back into the ground. They discharge the water into the next river. Then this fifth generation network in Heerlen in the Netherlands. And then also heat extraction from treatment plants, also done in the UK. And then the last one, the mine thermal energy storage, where we store surplus heat, in our case, from data center and from cooling and heating facilities inside the flooded underground mine. All right, so this was the first 101, and Gareth will now go more into detail in his presentation.
Thanks so much, Elke. I'll just share my screen, and if you give me the thumbs up if it's working.
Yes, we can see it, Gareth.
Wonderful. Okay, so first, thanks so much for the invite to speak at this, and it's an absolute pleasure to speak as a double act with Elke, someone who we really recognise as being an expert in the field. So thanks for that opportunity. So I'm going to talk about operational mine water heating schemes. My name's Gareth Farr. I work for the Mining Remediation Authority, which covers Great Britain. We're an organisation that manages a lot of the legacy of mine workings and incidents around that, planning and so on and so forth. But we're also trying to turn a lot of that legacy into a kind of a positive future as well, where we can look at mine water heating, cooling and storage and really put that into the public sphere and deliver some schemes. So hopefully that's what I can tell you about now over the next few minutes. So like Elke, I also used that recent paper as well. I may have come up with slightly different numbers, so we obviously need to have a little bit of a chinwag about that. But this map really shows the kind of countries that have got some mine water heating schemes. These are specifically coal mine water heating schemes. I think in my sort of literature search in the past, I think the first one was from 1979 in Wyoming in the United States of America, where there was a cigar factory that used mine water to cool the premises, which was quite interesting. And there's obviously schemes that Elke had mentioned as well. There's a well-known one in Canada as well, in Nova Scotia. There's the northern Spain, the Heerlen heat network as well. Also several interesting schemes in China. So there's also a couple of other great reviews, global reviews there I've listed at the bottom, should someone want to get that large picture of what's going on across the world. So let's come back to Great Britain, which is clearly the area I'm slightly more familiar with. We've got a little table here that really shows our live schemes with the red dots, and I'll describe a few of those. We've got some schemes that will be live soon with a sort of a yellowy orange dot. A couple of decommissioned schemes as well. And I think also dotted in between all of that as well are lots of closed loop borehole schemes as well. Now these don't abstract water, they're closed loops all grouted in, but they're quite numerous. What I should say, the map on the left-hand side is obviously Great Britain. The green areas are pretty much our coalfield areas. And if your geography is okay of Great Britain, you'll see that for a lot of these coalfield areas do have large cities on or around them. So example from Scotland, you've got the central belt between Edinburgh and Glasgow, where all our colourful dots are in the northeast of England. You've got Gateshead and Newcastle, plenty of large cities through the middle of England, and then down to South Wales, where I'm based, and speaking to you from today. So let's have a look at some of the things we've actually delivered. So I choose this example first. This is a company called Lanchester Wines. They were the first one in the UK to have megawatt scale heating schemes. And for me, what's interesting about these two schemes that they run is that they were both privately funded, which is really exciting. And they've also both been delivering heat to large warehouses that keep a lot of wine and other types of drinks like that at optimal temperature. So obviously everyone should drink responsibly, but it seems like a nice little use there of mine water heat, and something that's also beneficial, I would hope, to this company as well, which has really been a forerunner in mine water heat in the UK. So plenty you can read about that system, or those systems, sorry, there's two. Going totally to the other end of the scale now, this is one we did down the road from me not so long ago, where we actually put some heat exchangers directly into a mine water treatment scheme pond. So these large concrete feature you can see here as part of one of our 80 mine water treatment schemes we operate across Great Britain. These are the settlement ponds where we allow the iron to drop out of the solution in the water. So just by placement of this small heat exchanger, we're able to provide heat to a warehouse and some offices nearby. It was kind of a demonstration really of the technology that can be installed quite quickly. It only took really a tiny fraction of the heat available at this site, but has proved to be quite a useful demonstrator. This is another scheme that is, I call it under construction, but I would say it's actually constructed and very, very near to going live, hopefully. So just like our friends in northern Spain and elsewhere, we have lots of mine water treatment schemes. And this one pumps from a shaft, which you can see illustrated here. And we actually treat the water in a large kind of warehouse facility, and then the treated water goes to sea. So this water is coming out at about 20 degrees constantly, maybe 90 litres per second, give or take. So what we wanted to do here is get extra benefit from this place where we were treating mine water. And so a project that's been going on for several years with the council, Carbon Homes, Ash Group, and so on and so forth, we'll see now. The energy centre is in place. So on the left-hand side, the sort of modularised energy centre was put into place. This is adjacent to our mine water treatment scheme building, which is just out of shot. And then there's 750 social homes that are currently in construction and will be shortly connected to this mine water heat network. So very exciting. And I can assure you all, it is always that sunny in the northeast of England. It's a great setting there right by the beach as well. So a really cracking place to be, and a scheme I'm thoroughly looking forward to going officially live. And then this brings me on really now to what I'll talk about in more detail, which is our case study, which is the Gateshead Energy Company heat network. So Gateshead is located in the northeast of England. You'll see the little red arrow on the map there. Gateshead and Newcastle are side by side. So the river you can see here is the River Tyne. Just to the east of that is Newcastle. So if you're into football or things like that, you might know of Newcastle Football Club. But if you literally just walk across the bridge, you're then in Gateshead, which is this area in the foreground. I think what you can take from it is there's a lot of urbanization there as well. There's a lot of this area is underlain by mine workings dating back a few hundred years as well. There's clearly mixed use buildings on there as well, which we'll talk about. And the areas really you want to focus in on this are this little red box, which is pretty much where our boreholes were drilled, and we'll talk about those. Oh, sorry, blue box. This blue box here, which is the Mine Water Heat Energy Centre. And this little blue box here, which is part of the old heat district heat network, which was powered by gas CHP, but it's still part of the current setup. So let's dive into a bit more detail on this project. So the project is run by Gateshead Energy Company. They're in effect if you like, a spin out from the council. So they've been set up as a company to run this heat network. As I said, there's already a heat network there. So it is a combined heat and power heat network powered by gas. But they really wanted to decarbonize the heat element of this. So they wanted to see if they could move to mine water as a heat source. So we were really happy to support them in that journey. It took about 3 years to go from initial discussions to delivery of the mine heat concept. So Gateshead Council have really done a huge job with this. In terms of funding, I think the total funding that I'm aware of for the wider project is £15.2 million. And you can see below is some of the breakdown in costs there. So there is a cost for the drilling and the heat pumps, but a lot of other civils and buildings as well. And I think the heat network consists of over 5 kilometres of pipe work as well. So it wasn't all for the underground element. So let's dive in deeper. So this is our area. These two little blue buildings here are the ones I showed you in the earlier aerial photograph, the energy centre, or the 2 energy centre buildings. So what you can take from this map is actually most of the area is underlain by mine workings. This sort of orangey colour is what we call probable unrecorded workings, which means there can be a lot of workings in the UK that we don't really know if they're there or not. You can see our target seams with a high main, which is records going back to the 1770s, and the Hutton, which is the new one, if you like, we're down to which is from the 1850s. So you're seeing we're dealing with fairly old stuff, and it wasn't always a legal requirement for mining companies to deposit plans with us. So we do end up with a lot of areas where we think there's mine workings, but we don't really know until we've drilled into them. In terms of the hydrogeology, pretty shallow water levels. So, you know, we were anticipating favourable pumping heads, which is a good thing. The area is tidally influenced as well. I mean, I don't think that matters, but it's just a description of the area. So you do see tidal responses in the mine water heads. But definite challenges are shallow workings, old workings, and unmapped workings. So there's a mixture of everything there. So these challenges will come to bear their sort of fruit shortly. And I should say our target seams were to abstract water from the Hutton, which is about 150 meters below the ground, and return it to the high main, which is 50 meters. I'll show you that in a little cross section shortly. So here's our borehole locations. It's kind of classic brownfield site. We're adjacent to our energy centre. And what you can see here is we did pepper the ground with quite a few boreholes. Now, they weren't all successful, and that in part we knew would be the case because we were drilling in an area with very old records. But we were able to get boreholes quite close to the energy center, which is this building here. Unfortunately, the ones that were really, really close to it weren't successful, I don't think. So here's a little table summary of what went on. So as far as I know, it was £1.8 million for drilling. We drilled 12 boreholes. 7 of the pilots were abandoned, and again, mainly for those reasons that simply the workings were so old and poorly recorded that there was a stroke, an element of luck if we were successful or not. But we did end up with 6 useful boreholes, 5 of which I've listed here. Or did we end up with 5? Anyway, there's 2 abstraction boreholes, a primary abstraction and a backup abstraction well as well, just because you want resilience in the system. We've got a borehole to put the mine water back into. We got some monitoring boreholes, and then we had another borehole that interestingly sort of connected those 2 seams a bit closer to where we needed to be. We just found it really helped with the pumping of the lower seam. The pumping tests were up to a constant rate of 140 litres per second. Clearly there were step tests done in the run up to this to fulfill all the environmental permissions and so on and so forth, but the max rate was 140 litres per second. This is a photograph here of Jim Gillen on the right, who's the head of Gateshead Energy Centre's phenomenal work in this area, and the local councillor as well, who's been hugely supportive. And this, I mean, you'll all know what a borehole looks like. The borehole is the small circular feature below the sort of blue pipe work. This is the kind of rising main stuff going into the system, and this concrete O-ring is just purely there to house various electricals and so on and so forth. This is covered up with a manhole cover, and you won't even see it if you walk on top of it. So a small footprint for sure. So for those of you that are interested in regulation and licensing, or even if you're not interested in it, it's still important. So what I'll say is we have made huge leaps and bounds in Great Britain with trying to formalise and get our approaches in order. So in Great Britain, we tend to have the environmental regulators, which in this case is the Environment Agency, but also ourselves at the Mining Remediation Authority, who own, on behalf of the UK government, the majority of coal mine workings. So we also, in effect, are, if you like a landlord for the mine workings. So we also need to grant permissions to access them safely. So this, I don't expect you to take all of this down, but if you want to know more about how we've streamlined these approaches in England, there's a link at the bottom. You can have the slides after, and that will take you to a combined process. But in effect, we have our pre-construction, so we have a lot of pre-application discussions with all the various bodies. Then with the Environment Agency, we look at our groundwater investigation consents, and also with ourselves at the MRA permits to drill. And there's various access agreements. And then we get on to the fun bit, drilling of the boreholes. And then we're in the testing phase, so we're doing pumping tests and monitoring and so on and so forth. And there's, again, various permissions to have in place for that as our pumping test. And then we'll be obtaining kind of finalized licenses and permissions based on the results of pumping tests. And then hopefully once you get to the end, and I should say this is a very simplified timeline, once you get to the end, then hopefully you're up and running, and then you've got your sort of ongoing monitoring, which needs to be reported back to the environmental regulator and ourselves. And hopefully you're just up in a nice, happy place of operation in a nice, stable, sustainable manner. So that's kind of the dream, and that's the process, and you can find out a lot more detail below about that. So here we go. Let's get back to the fun stuff. If there's any geologists in the crowd, which I'm sure most of you are, apologies for this very simplified section, but hopefully it conveys the right point. So here's our 2 abstraction wells, which are going down to the Hutton seam. It's about 150 meters below. They dip off to the east. And then we have a recharge borehole where the thermally spent water comes back into this higher seam. Obviously all the water comes up into the energy plants and then it's returned, so no mine water is going into the homes or the businesses. All that heat is transferred to a clean loop of water. And then we have this borehole further off here that joins these two seams at a closer position. So not always the most ideal thing on paper, but we did really need to improve the efficiency of pumping from the lower seam, and that did provide a much better transmissivity and much better pumping effect during the pumping test. So these seams are joined anyway, just at a further away point. So this just kind of aided in that circulatory flow that we needed to achieve. So these things make me incredibly excited. It's been a long, long time waiting to see a large building in the UK with the words "Mine Water Heat Pump" slapped on the side of it. So the first time I saw this, I was jumping for joy, which is, I don't know, it's maybe the geek in me, but it was just super exciting to see that, and that Gateshead Energy Company had put those words on the side of the building, big proud letters, and that really is super exciting. But that's the main building there. You can see it's not that huge at all. It's just on this corner of land here. I think this is a council depot. The boreholes are just off picture to the left, and you can also see the solar farm at the edge of the solar farm there as well. Interestingly, this company that is just based behind here, so you can see these sort of grey storage tanks. This is a really well-established company up here called GB Lubricants. They in fact sell lubricants into the industrial market. So their whole business is based around hydrocarbons, but they're connected to this mine water heat network, and they've actually been able to lower their carbon footprint on what is ultimately a lubrication business, and that's helped them win more contracts. So a really great little story just for that business that's next door to the energy centre. So what does it look like in Hull? I mean, here's a sort of a shot of what's going on at the moment. So there's over 600 residential properties connected to the mine heat network. There's 24 large buildings, so most of these big ones you can see here in the foreground. Also include some large conference centres like the Glass House or the Baltic Contemporary Arts Centre. There's also a college there as well that's being heated, and all these council offices as well. Warehouses and light industry as well in the foreground. So, you know, I think it's super exciting. It's definitely showing it works at scale. I think without putting words forward for Gateshead Council, I think they perhaps would stress, at least in the UK, it's still really useful to have some of the enabling funding in place to make all heat networks work, just because you have obviously the high upfront capital you need to cover. And some of these funding streams seem to appear and disappear. So that kind of support is still useful. But I think in terms of returning much better carbon savings than perhaps the air source equivalent, and also what I haven't really touched on is it really connects the heritage of a place with the end users. And I think from what I've seen, there's a lot of pride in the local community that the historic mine workings are being repurposed for a green future. So I think that story is something we all need to cling on to, because clearly you need public support to make these schemes work, and so that is quite a vital element. So I think that might bring me to the end of my slides, possibly on time. So what's the future for mine water heat in Great Britain? We've got lots more work going on, as I am sure do some of the private companies working on this as well. We've got a leisure centre that should be live soon, and we're also drilling at a large general hospital shortly. So to deliver heat to the NHS and to large hospitals would be really special, I think. Future opportunities, we want to really get into exploring shafts for quick wins where drilling isn't required. Projects we can deliver quickly without drilling are always going to be a good thing. There's some talk of using mine water for hydrogen via electrolysis, and I know that in northern Spain they're actually trying that out in conjunction with their existing mine water heat network. And also interseasonal heat storage in mine workings. And that leads me to seamlessly hand over to Elke, who will talk about just that, I believe. So Elke, over to you.
Absolutely wonderful. If you can close your slides, I can open mine. All right, and here we go. Can you see the slides? Okay, cool. So, mine water geothermal storage, MTES, is the last topic today, and I would like to introduce to you our European funded project, Push It. And Push It is not that song from the 80s, 90s, I'm not sure. In this case, it stands for Piloting Underground Seasonal Heat Storage in Geothermal Reservoirs. And the objective is that we know there is a discrepancy between heat consumption and heat availability. So we need storage solutions. And for this reason, we wrote a proposal to investigate certain ideas or certain concepts when it comes to underground heat storage. And we wanted to have a large scale application of high temperature heat storage. And now the important word is high temperature, because low temperature, and I've explained just now, is done already in several cases, but not high temperature. So we chose 3 different locations for pilot plants and 3 different follower sites. You can see them here. It's a European project. We are in Bochum, Darmstadt, United Downs in the UK, Delft, Netherlands, Berlin, and Litoměřice in Czech Republic. And in the project, we have ATES systems, so aquifer thermal energy storage, BETES systems, borehole thermal energy storage, and MTES, and this is what I will talk about because we talk about mine water, mine thermal energy storage systems, and ours is here in Bochum, where we are located in Western Germany. This is an image or photograph out of our meeting room, just like 5 meters down the corridor. And you can see the technical center of the nearby university. And what can you see? 2 chimneys with smoke coming out, or steam in this case, rather. And the one on the left side is from a heating facility. And the one on the right side is from a cooling facility. In fact, these are 2 cooling towers, 2 11 megawatt cooling towers. So what's happening here? Heating and cooling at the same time. Makes no sense? It makes no sense. So what can we do? There's obviously excess heat, but it's not stored. It's just blown away. But underneath that facility, the technical center of the university, there is a large mine, and the mine is called Mansfeld. It's just the name of an area. And here, this is the entire Mansfeld colliery, but here we have a small isolated area that was never in operation, but it was used during World War II as an underground factory for steel ropes, and it's in 120 meters depth with an estimated volume of 10,000 cubic meters. So we have this first level here in 120 meters of depth. So just keep this in mind. It's a large mine, but here for the storage solution, we just have this small isolated area. You can see this here. This is the huge university, the Ruhr University. Here is the technical center. Here's our institute. So we're just down the road. I'm currently sitting here in this building that is now built. So just, I don't know, 150 meters down the road is the facility of the technical center. And underneath the technical center, this is all the technical center here, is this former underground mine, this former colliery. You can see the 2 parallel galleries, so they're both on 120 meters depth. And we have excess heat from a data center, from a combined heat and power unit, a CHP facility, and 3 additional gas-fired boilers. And we have the mentioned cooling towers. Remember that photograph, these were the ones on the right side, each 11 megawatt. So we I have one more image here, exactly. So we thought about, okay, we have this mine here, we have surplus heat from the data center and from the CHP unit and from the cooling towers. Let's drill inside the mine and let's install a mine thermal energy storage facility. So we have 4 drilling points. That was the original idea. Then the drilling work started in September, and we first drilled one monitoring well. We actually wanted to drill into the mine, but they didn't work quite well. So we decided, okay, the first one will be the monitoring well. And until now, we have 2 more boreholes, as I said, in 120 meters depth into the flooded mine, and have some pictures for you here. So here you can see the drill rig in the background with the conductor and the drill pipes. And just to mention, we have our own Institute drilling rig. It's a 30-ton drilling rig, which is absolutely fantastic because we don't have to hire a drilling company. And because it's a research project, we can really try out and modify a few things. And we have so much learning because drilling inside the mine is not so, let's say it's quite different to drilling into the normal underground, because you don't really know what you can expect with the mine workings and what conditions the mine workings have and if the plans are accurate. So it is really nice that we have our own drilling rig. Here you can see my colleague Stefan analyzing the rock cuttings. You can see a wire-wrapped screen tubes for the second borehole. So we use these wire-wrapped screen tubes, and we installed a PVC filter. This is now a picture from the observation well. And we did not use steel casing, and I already saw one question in the chat. We can talk about this later, but in this case, we decided for GRE casing, so basically plastic, to have less corrosion effects that could occur with a steel pipe, because we also didn't know about the mine water quality. You only know once you drilled inside the mine. It could be really high mineralized mine water, it could be acidic mine water, or the mine water could have groundwater quality. So you don't really know before you drill. So in this research project, we had the opportunity to test out the GRE casing. Then we also did some geophysical logging. You can see on the left side a picture of the gamma ray and the deviation survey. So this is the geophysical tool with the centralizers. You need the centralizers that the logging tool is not wobbling around inside the borehole. I really like this image in the middle. It's really interesting to stand there and look down into this dark hole. And what else did we do? So deviation to see the incline of the borehole, because it's a learning process. Gamma ray, then acoustic borehole televiewer, optical borehole televiewer, and we also took water samples with a fluid sampler from the flooded underground mine. And here on the right side, you can see a picture again of the drill rig and us early in the morning setting up our fieldwork equipment. Here one more picture that was also the one on the beginning slide. This is from the camera survey or from the camera inspection when we were tapping into the flooded mine void. And if you go onto the website of the Mining Remediation Authority, they also have some really nice videos from going down the borehole into the mine. Highly recommendable to watch. So here I told you we did some derivation assessment. And this is now from P1. This is the one where we did not hit the mine. And you can see that there is a large incline, and the borehole did not go down straight. And we have had a really large incline. So how did we solve this problem? We later used heavy bars and the pendulum set for the stabilization. So basically we had heavier, extra steel pipes. Sorry, I'm not a drilling engineer, but yeah, so to stabilize the entire drilling system, that you could really go down vertical, and there was not a large incline into the mine. This is a picture of the water sampler. First, we had a bit of a makeshift sampler, which also worked very well, but then we ordered a depth-dependent sampler. So now on, if we, for example, want to measure in a flooded shaft, we can also measure at different depths. But interestingly, while I talk, you can also scan this video. It's a little video where you can see the sampling work. Interestingly, the mine water had groundwater quality, and these are not just 4 parameters from the in situ measurements, so 13 degrees Celsius, 850 microsiemens per centimeter. This is a bit higher electrical conductivity than groundwater, but it's still completely fine. Oxygen 5 milligram per liter and neutral water. So no acid mine drainage or anything. And this is also what a lot of people think, that mine water is always highly contaminated, super high mineralization, but this is just not always the case. You have very, very different mine waters, and it's really site dependent what you have to deal with. So just to clarify this. So what's the next steps, and what are the lessons that we learned? The next steps is that we want to complete boreholes number 4 and 5. These are on the other side of the technical center, and then also again conduct geophysical logging, camera runs, microbiological investigations, and geochemical sampling. With the microbiological investigations, we work together with our project partners from the French Geological Survey. And because we don't really know with the heat storage how the injected heat will also affect the the microbiology inside the mine environment. Then now this year we will soon start with circulation performance tests, and then hopefully end of this year or beginning next year we will connect the ground workings to the technical center, and we will test the entire MTIS system. What's ongoing work? We have co-simulation, so it's not only the field work and installing this pilot plant, but we also do co-simulation and numerical modeling. In our case, we use Spring for the hydraulic modeling, works very well for flooded underground mines. And as Gareth also said, engage with the community and bring acceptance for new technology is really, really important, because if we want to implement mine water geothermal systems in a larger scale, first of all, people need to know about it. This starts with power suppliers. When they have to do their heat planning, network planning, they need to know that they can utilize flooded underground mines for mine water geothermal, and a lot of people don't know. But then also with the public, it's just important to inform the public if there's a big drilling rig, what's actually happening there. So what we did is we installed some fence banners, or it's now in German, obviously. So one with general information, but then we also thought, okay, there are a lot of people walking there with their kids along the fence, so why not also have a fence banner for kids? And then it's also usually easy for people to read that maybe don't really have the deep technical understanding. So anyways, we included a little experiment about heat storage, and we will install a plastic pipe filled with the cuttings so that people really can see the geological layers that we found there during drilling work. And then also one interesting idea, I think, is that we installed a sign in 120-meter distance, because a lot of people, they don't know about distances, and we tell them, okay, we drilled 120 meters deep, but what's actually 120 meter? So just a few ideas. And then we also made a children's book, a small one, about underground thermal storage, in our case about the MTIS technologies, and we just made a kind of a real story that a father is there with their kids, and then they see the drilling site, and then they go into the camera van and they do like a camera survey inside the flooded mine. All right, a few lessons learned from our pilot project with the Enter systems in Borum. So stakeholder management is very, very, very essential. And that's right from the beginning. You have to talk to a lot of people because this is a big project and a lot of people are involved. So it needs to be done very well. Planning is time consuming, especially when it comes to regulatory questions, because this is a new technology and responsibilities are not necessarily clear. So this is a very time-consuming process. And as I said here, early consultation with responsible authorities. It's important because you're sent from there to there to there to there and then back to them. So yeah, early consultation. We adjusted the drilling method and we made sure that we avoided deflection of the drilling. And it would be actually really, really nice if we would have a little underwater robot that we could let down through the borehole and that the robot could float around inside the mine, because we would like to see if the weather doors between the two galleries, so they're usually big steel doors, if they're closed or if they're open, because if they are closed, our hydraulic system is completely different than when they are open. And if you would have a little underwater robot, which we don't have until now, so maybe you have some good ideas or you know someone, that would be fantastic for future work. And I think we might need this also when mine water geothermal develops further. All right, last slide. I guess a lot of you know a lot of students. So in June, July, we have a summer school here in Bochum from the Push It project, not only about mine thermal energy storage, but also about aquifer thermal energy storage and borehole thermal energy storage. So yeah, if you're interested or if you know someone who would like to participate, you can check out the Push It website or follow Push It on LinkedIn, and then you will see advertisement for the summer school. That's from my side. Thank you very much.
Thank you so much, both of you. Well, really nice presentations and perfectly matching together, also timed. Yeah, before I start asking my tons of questions, we have a few questions in the chat, and I would start in the order of how they were asked. So Ardi Manto, you may be first to ask your questions. I hope I pronounce it correctly. Ardi Manto?
Yes.
Yeah.
Okay. There are two questions actually. The first one is related to the corrosion effect to the pipe maybe, but you have explained, but maybe you could explain again so that I didn't recall that. Can you say that again? And also, what type of mining actually you use at the current situation, whether it is from the coal mine or the mineral mine like gold and copper mine. That's all. Thank you.
So yes, there are corrosion effects. This is why I explained that we did not use steel casing in our project, but GRE casing. And there are also especially corrosion effects in the heat exchangers. But yeah, for example, our colleagues from the Freiberg University, they are technical process engineers. They are trying to install a pre-treatment system so that you avoid a lot of corrosion in the heat exchangers. And to your second question, we can do mine water geothermal in all sorts of mines. Until now, we focus a lot on coal mines because they are usually deep, and these are also the recent mines. But there are quite a lot of examples from mine water geothermal in former ore mines. So at the moment we are doing quite a lot of opportunity or potential studies for former coal mines here in this former ore mines here in this area. So examples for ore mines are there as well. Gareth, do you have to add something?
No, I think that's a perfect answer, really. We're also seeing that in the UK as well, where there's some small mine heat schemes from non-coal mines, so from metal mines, and hopefully soon there'll be some bigger ones from metal mines. So yeah, it's not just for coal mines. Anywhere where there's water, and if it's in a mine, well, even better. And corrosion, I think as well. We've got quite variable mine water chemistry. Some of our waters is incredibly corrosive, and others is actually really just quite fresh. So it depends where we are, and we use different management techniques to kind of reduce the corrosion in the worst places for sure. But in some other places, the biggest challenge will be, ochre and keeping oxygen out of a system.
Yeah. Did this answer your questions? Obviously. The next one would be Anke. You're muted.
Sorry. And of course, I have questions with respect to rock mechanics. You said that you're basically placing well bores and you're using the systems in urbanized areas. So I was wondering, how is the stability of the surface ground? And I'm thinking very much about Bochum, where you have a lot of those sort of shallow collapses at the surface, but also deep collapses, even without any usage of the mines. So how are you addressing those surface collapses, larger mine shaft stabilities, and also the stability of the galleries? Question is, have you observed or are you monitoring ground movements? Do you see any sort of changes related to the water circulation and the changes in pressure that comes with circulating water and the different temperatures of the water?
Yeah, so I think first of all, it's important that when we take water out for mine water geothermal use, you can imagine more than or like putting a straw into a full bathtub and taking a little bit out, nothing really happens. It's not like when you pump water for dewatering, then you have really, really big circulation systems. But for mine water heat, this is usually not the case because the amount of water that we take out, it's not the entire volume. So you have to see the ratios. So maybe you might think there is a lot of water movement, but actually there is not that much water movement. But we monitor, and now, for example, in our case with the EMTA system here in Bochum, we installed the mint barrier system. I posted a link into the chat. It's developed by the Technical University here, and it's installed on, you can install it in the surface, but usually on former shaft openings where they close down the shafts on top. So if there's any ground movement, these monitoring systems will give alarm, but until now we did not detect any movement.
Thank you so much.
Mm-hmm.
Maybe before I go forward to Scott, one question which settles on top. Did you already check the temperature development inside these mines? How does this change in the mine and maybe also adjacent to it in the rock mass?
Yeah, we use glass fiber to monitor the temperature change. But yeah, until now we call, well, our system is not yet running, our EMTA system, so we don't have monitoring data from a running system. But since drilling, temperature just stayed the same.
Okay, great. So I think the next one is Scott, who has some questions for projects abroad. Scott, may you unmute yourself, please?
Hello, everyone. Thank you for them very interesting presentations. The question I have as a drilling contractor, we have a lot of health and safety around gas management during these drilling projects. I know I've pretty much drilled all of the projects mentioned today, and there was a real focus on gas risk mitigation and things like that. I'm just wondering what technologies we are starting to look further afield and overseas for these mine water heating schemes as a business. And I'm just wondering what sort of mine gas risk management you have in place during the drilling operations.
Gareth, do you want to answer that one?
Well, I mean, I think I've worked alongside Scott in the past, has always worked on similar projects. I think we're kind of up to date on the UK stuff. Is that right, Scott? And you're reaching out to the wider community to see what they're doing, as in abroad, as in not in the UK. Is that correct, Scott?
Yes, that's right. We're looking to start
Sorry, so
offering services.
I'll throw that one back over to you. Elke and Co.
Did you have gas control on the wells you drilled for your project, or were you confident there was?
No. We had gas control all the time. All the time
Yeah.
when we were drilling, we had gas control just with a handheld monitoring system, and we also installed. Oh no, sorry, I don't know now the English term, but the pipe where you lead the gas away. And then when we were working now, for example, during the geophysical logging, we installed big ventilators right at the borehole to blow the gas away from us.
That's great. Thank you very much.
Yeah.
Maybe they're also on top of things where you're required to install some seismic monitoring for the mines, so which is somewhat connected to what Elke asked before, but so in case something collapses.
Who do you ask this question to?
Both of you.
Shall I? Well, I mean, I can build on that, the previous kind of question. We have obviously ground movement comes up, and it's something we take super seriously across the coal mining areas because of collapses, historic workings, and map workings, so on and so forth. But we have been looking using INSAR data from satellites at ground movement in an area where there's 3 large megawatt scale heating schemes. And thus far, although we haven't published any results on that thus far, I don't think we've seen anything relating to the pumping of the water, any ground movements relating to the pumping of the water. But I'm sure, like just the same in Great Britain as it is elsewhere, we do see other kind of rebound effects from coal mines as they fill up and the ground moves up, and also in places subsidence effects. So, but no, we haven't knowingly identified something from pumping or recharge of water to date for mine heat schemes in the UK. Not saying there won't be any, just saying we haven't seen any yet.
Thank you. There is another question from Aris. Aris, may you unmute yourself?
Hello. My question is about the well design, because you used the GR casing. It's but I'm working here in Arizona, and I'm just curiosity about what kind of filter pack or how you seal the wells to keep the well design.
Yeah, so I'm not an expert in the well design, and I'm also not the project engineer for the project. So in the comments I sent my email address, and I would like to forward your question to our project engineer and to our drill master, because they did the whole well design and they can give you all the technical details. Sorry for that.
Oh, no, thank you.
Yeah. So something you mentioned is actual positioning of the wells. Did you do some investigation, geophysical investigation, where the old mines are, or is it just based on the old maps, mining maps?
In our case, it's always just based on the old mining maps. We don't do any
I can't hear
geophysical.
you if you are answering.
That's strange. You should. No?
I hear you well.
Okay. So Peter, it's on your side. But I will still answer the question. No, we don't do geophysical logging. We purely rely on the mine plans, and they are usually, well, for the cases we had until now, they're very, very accurate. But the mines we drilled into so far had more or less current mine plans, so no from 1700 something, because these plans are usually not that accurate. For the plans from the last 150 years are very accurate and reliable, so there is no need for geophysical logging.
Yeah, so Gareth, you mentioned, I think, that you had some issues in the Newcastle area, right?
Yeah, that's correct. We had issues, but I think we also knew we would have those issues. So we used the mine plans to the best of our ability, noting some of them were incredibly old or there were none there. But we didn't use any surface geophysics to identify the workings, probably no. But we obviously did, no, we didn't. We used the mine plans or other kind of knowledge like that.
Thank you. Anthony, you already switched on your video.
Can you hear me? Yes.
Yes.
Sorry. Yeah. So yeah, thank you. It's been really, really informative. As I say, this is not a geologic question. I'm just more interested to know, like, what's the barrier from preventing more of these projects getting up and running, particularly in the UK? Is it a matter of, funding, or is it something else entirely?
Yeah, so I better take this one, I guess, for now, and then pass it over to Elke, perhaps for the German perspective. So thanks, Anthony. I think one thing I always say to myself is actually, the UK does have quite a few of these schemes up there with the countries like Germany and China in the world that do have quite a few of them. So I don't think per se they're being prevented, but I think what I would say from when I'm chatting to lots of stakeholders and customers is often finding that capital for the early stage drilling. If you can connect to an existing treatment scheme, you might remove that need. If you can use a suitable shaft, you might remove that need to some degree. But is that early stage capital? And we've had some good funding streams in the UK which have been closed and open, different ones opened, and we had the renewable heat incentive. I realise these things don't mean much to the global audience, but we had various parcels in there that would enable this, but they keep chopping and changing, and some sort of certainty, or maybe even like perhaps you see in the Netherlands, or I think more recently Germany, some sort of government underwritten insurance scheme to allow you to drill these wells but not take all the risk yourself would probably be quite good. Because clearly the want to do it is there, the vision to do it is there, and people have done it and realised it at scale. But it's often, where do I get the cash to drill a borehole? Is the early stopper.
Brilliant. Thank you for that.
Elke, I don't know if you've got
same here.
views.
Same here. It's exactly the same here in Germany. So the in-front investment is a problem, but also really the people don't know about the technology, and decision makers don't know about the technology. And it's now more and more coming in the last years, and especially in the last 2 years, we were traveling around everywhere, and we went to every conference and talked about mine water geothermal. So it's changing a little bit, but it's just, there is no knowledge that this is a possibility for heat planning.
Yeah, I've just been at a conference this weekend talking to people, and just the amount of people that just do not know about it. There's a lot of potential, particularly in I mean, Gareth, you'll be familiar with Wrexham. There's a lot of potential around particularly the west side of Wrexham there. And I was talking to Wrexham councillors, and they just do not know about the technology.
Yeah.
Are there other commercial boundaries which you are hitting beside first money seed, essentially?
I would say the public perception is really good about it. So this is nothing we have to worry about it, because people are always really happy when they hear, oh, we used the old mines and there's this heritage and now we use it. So it's not so much of a burden anymore, but we can do something with it. So the public perception is on our side, like we are on the good side.
Yeah, it's quite often the challenge for mine water heat, I think, is that, unlike a lot of groundwater issues, they're out of sight, out of mind, so they're below the ground. But I always say that's the benefit as well. You know, the benefit is actually you don't see them, and you don't seem to get the opposition to that as you would do to, you know, windmills and solar farms and all these things. So that's a benefit, but it's also a challenge because you can't see where it was. That's why I thoroughly like that picture of the energy centre in Gateshead that has the big sign on saying mine water heat building, because it's one of the most visual things you can see on our side of the world, that there is something there.
Thank you. Aris, you have another question. Hi, nice to see you.
Yeah, just I'll try to start my video happen. Okay. Hello. It's very interesting. One of the slides, they have a mine water heating scheme. It's a map. It's a world map. But it's curiosity. All the red areas or market areas are above the equator, and nothing is below. Yeah, it's just say that. My question is, what is the reason that all the mine water heating source technology or application is just in wealthy countries? Is because what is geological features? Is just by technology, politics, or cost? What do you think about that? I'm Mexican, sorry, and I'm mine geologist. I work in hydro, geotechnical, and everything, and I'm senior geologist. And I'm curiosity why is this kind of application for mine water is just in riches or countries. It's not complaining.
No. There is an easy answer. There is a very easy answer to this. It's warm there. You don't need to heat. Not everywhere. Obviously, there are also parts in Southern America where it's cold and where you would need to heat in winter. But like I lived and worked in South Africa before, and if I tell them, oh, mine water geothermal would be interesting to you, then they say, yeah, for what? Because we don't need to heat. And until now, most mine water geothermal applications are for heating and not for cooling. So maybe if this changes a bit, that you can also use it for cooling, that would be something different. But in maybe less developed countries, the problem is that providing power is more a problem than providing heat. So people come to us and say, no, we need power, we don't need heat.
Okay, thank you.
Elke, another question from your side.
For me, right?
Yeah.
Yeah. It's just more like a comment. What I like so much about this is that you can actually have heat generation very close to urban areas, and that means you don't have long transportation networks that you need to build. And then, of course, comes the repurposing of existing infrastructure, and the addition of the infrastructure that you have to do is extremely limited. So as you said, Gareth, the visual impact is not the same as for big wind farms or something. But if you would think about on something you would want to improve, make it even more efficient so that you can, I know you showed very large buildings you can heat with this, but is there something else that could be done? Could we think about converting this heat into electrical energy? Right, so the wind turbines are always a big discussion, but if you have a network of mines all around the country, like you have in UK or in some areas in Germany, you have loads of mines in China, you have a lot of mines in South America. So if you could convert that heat into something else, in another energy form, then suddenly we may take off more than currently. So what is your take on it? What could be done?
Gareth, would you like to start?
I haven't seen many ways that it can be done in the UK to turn it into electrical energy, but I'm aware of some sort of high heat difference devices that can generate some electricity, but you need a fair difference. But I think your wider point is how can we perhaps integrate it with other co-benefits to make it more attractive, and perhaps watching what they do in northern Spain with their hydrogen generation from mine water alongside their heat network is one I'm watching really closely. Often people ask about critical mineral recovery from the water as well, of which it's probably not going to be huge in the UK, but definitely one that's worth looking at, just to rule it out. And then I think always just not seeing mine water heat as the only option. Now we could have mine water heat connected, like Elke says, to data centers to buff up the storage. We could have it connected to other heat sources. It doesn't have to be a one-trick pony. It can be part of a wider system, and that's probably where I'd like to see it in the UK.
Okay, thank you.
I think we first need to consider how we, for example, run our pumps. So for mine water, if we don't use the edit, but then for the other systems, we always need electricity. So first of all, we can think about where do we get the electricity from to run the pumps, and this could be electricity from solar panels, or this could be electricity from turbines. When you inject the water back into the mine, you could run turbines so that the entire system is more self-independent. I think this is the next step to look at, to make it more efficient also. So we need to think about where to place the heat exchanger, if you want to have the heat exchanger at the surface, or if there might be better locations for the heat exchanger. And our research group is in fact also looking at the electricity generation idea. There are several systems that work with higher temperatures to use warm water to generate electricity, but we are doing now some research to see if we can also use lower temperatures. Yeah. But I think the key point for now that we need to focus on now is to have a better interplay and to run, for example, our pumps also with renewable energy.
Okay, thank you.
Thank you a lot. Looking at the clock, I think we are close to the end. So I would actually everyone like to join me for thanking the both of you. It was a great talk, was a great discussion. Thanks a lot to share all your knowledge.